Hello viewers, welcome back to video tutorial on AgentGrid. So in this video, we'll be discussing one other pattern. This is the third pattern. We have already discussed two patterns before this video. So right now, we'll be discussing a parallel agent workflow with the open source AgentGrid SDK. So in this example, we'll be showing how parallel, basically fan in and fan out will come here. Parallel pipelines of agents will work. And the use case that we are focusing is a RFC, which is a request for comments, compliance summarizer agent. Basically, we will be doing an RFC summarizing. We are going with some new features, maybe for some of our project, and we require some comments on that. So that's what we are trying to achieve in this use case. So the rest of the file remains same as what you have seen in the first and second video. So basically, the RFC summarizer task using parallel agentic flow. We have a input RFC document or a RFC text is coming to the first agent, which does a fan out operation, and it also tries to do create a brief for each of the agent, because their agent, we have to define what they need to do, right? So this summarizer agent will try to brief what each agent pro or a con argument or a safeguard argument they have to do. So it will summarize the text and it will provide those text to each of these three agents. So these three agents will receive input unique for each of the agents, and they will work on that agent the task, and they will provide their views on the new feature request. And that will be later on mixed. A fan in operation happens here from this agent concept synthesizer agent. It will try to take all the data from these three agents and it will synthesizes or it summarizes the whole of the RFC, and then it gives the final consensus output. So this kind of use case will come wherever you are trying to, let's say, not just this use case. Let's say you have a certain task where you want to let's say you want to duplicate the same task with the different agents. Let's say maybe checking a bug in this agent with one model, or a checking a bug in with another model, or improving the document. Let's say you have three different models here, and you are trying to implement document content. So at the end, you have one more agent which will try to do a consist. So in such cases also, we can use a parallel flow or a parallel agentic pattern. So we have a summarizer agent, which acts like a splitter or a router or a fan out operation agent. It neutralizes the and structures the incoming RFC text and acts as an entry point, broadcasting the summary to a multiple parallel workers. And this is the code, the RFC summarizer. And next, I'll explain the code. Next is our parallel evaluation workers. So we have three workers. One is pro argument and con argument generator and a safeguard proposer. So it creates a Steelman case for the RFC and it identifies critical, the second con argument identifies the critical technical risks and downsides. And the third guy has to suggest the concrete constraints and mitigation strategies. So it will try to guardrail the new feature that is needed, what all guardrail is required. So it will try to do that. And at the end, a consist synthesizer, which combines the output from the parallel workers into a final recommendation. So since we have three sub-agents, we require a mux here. And since we know that there are three agents there, so I require a mux of size 3. So it basically it waits for a 3 input coming out, input coming from these agents, and then it clubs it and it gives it to the LLM to do a consist synthesizing. So let's go to the code. Yeah, before that, the config YAML, the agent config YAML, we have a RFC summarizer which will fan out to 3 different agents, and the pro agent, safeguard agent, con agent has a final agent which is consist synthesizer, and consist synthesizer doesn't have any other further agents, so I have kept a false. And let me go back to the summarizer. Summarizer has this signature, RFC summarizer signature, where this is the doc string of it, and it takes one input and it gives a summary brief. And rest remains the same as the previous video. We have a chain of thought here. We have a DSPy module which takes this RFC summarizer and also the instructions coming from the JSON file. and not this doxing is a dummy, the doxing I have provided, which is same as what we have in the JSON file as well. So these all are like a payload processor just to process the input, and a model context manager to handle the model that we wanted. And this model context will help in setting the model for a DSPy. And the sample agent, so we are initializing all the classes that we wanted, default messages, AIS, DSPy, LMs, and then in on data, so we are basically passing the text, input text, and from that we'll taste this text, we'll take this text and we'll give it to the LLM, and that will give us a summary text. From that we'll try to extract the summary, and that summary will be passed on to the next agents in a loop. So we know that there are 3 agents that will get it from the configure.yaml, and in a loop we are sending those details to those agents without any synchronization. Meaning without synchronization we will send it, meaning once the data is input is sent to the second the first agent in the fan out, we will not wait. This will not wait. It will simply send again second task to this. It will send second, third, data to the third agent without waiting for the response coming out of this, because it knows that this is not the guy which will send the output to the user, but the consensus synthesizer. So it doesn't have to wait. It will simply send the input to these agents and walk out. So this code is same as what we have provided earlier example as well. So next is a pro argument generator. You are a pro argument generator. Produce a high quality Steelman argument in favor of the RFC. Focus on concrete technical benefits, quantitative improvements, latency, cost, scalability, and the alignment with the long-term architectural goal. Avoid generic praises and be specific technical. So this is the system message for the pro argument generator, which does the pro argument generation for the given summarized RFC, and it will try to send it to the last agent. So next is a con argument. You are a con argument generator. Produce a critical constructive con arguments for the RFC. Identify technical debt, operational overhead, potential failure modes, and security blind spots. Challenge assumption, highlight where the proposal might introduce a complexity or a regression in performance and reliability. Basically it has to identify the negative side of it. So what will happen, or if we are accepting it, what all things that we need to take care. So it is again same. So it will do the give it to the LLM with the system message and the RFC summarized text, and then it will extract the output from the con argument, and we'll send the output to the next summarizer. So this is a safeguard proposer. You are a safeguard generator. Propose a practical actionable safeguards to mitigate RFC risks, and suggest specific observability hooks, SLIs or SLOs, automated abort criteria, phased rollout plans, and fallback mechanisms. So these are like guardrails that we need to provide to the RFC. So that will be discussed by this safeguard proposer. So it will also do the same thing as other 2 agents, where it will give to the LLM the text as well as the system message. It will extract the result, and it will be pushed into the kind of a structured string, where input to safeguard agent and output to safeguard agent will be constructed, and that will be sent to the next agent. The next agent is a consensus synthesizer. In the consensus synthesizer, since we need a mux here, we have a defined one class known as muxer, and in the init we have to provide the n here, meaning since we know the number of agents it expects input from, so we are passing that here. And I have 2 variables, packets and self.n, and I have a function here add. So for this add I need to pass on one key as well as a task, input task. So what it does is, if key is not present in the self packets, meaning first time whenever the first key, the new key is coming, and if that is not available in the packets, it will create that, it will copy that task to that packets.key dictionary. And if at all n is 1, then immediately it returns, because this muxer has to handle the boundary conditions, n equal to 1 or n equal to 0 or n equal to more than 1, all those things it has to handle, right? So if n equal to 1, we are returning the packets dot key itself directly. So because it doesn't have to wait for any more inputs or any more inputs to the mux, so it has to immediately send. If n is not 1, so then what we have is, we have just created this and we are returning a none, because it will come to the else part. I'm sorry, it will come out of this if and else condition, it will return a none. So in the reception side, it is handled that if it is none, don't do anything, just go with the again one more input, receive the input, and call the muxer dot add again. That's what we have written in the AgentGrid SDK code. So when a second input comes again with the same key and a new task, let's say first a pro argument is generated and it is coming to this muxer. Now a key is created. Key is basically a session ID kind of thing, and that whatever the output from the pro agent was there, that will be pushed into the packets. And when the con argument generates the output and it gives it to this the synthesizer agent, it will receive it, and that at that time this condition will not be met because key is already present in the packets, so it will go to else part. So in the else part, it checks whether text is present in the self.packets.job data, because this is the currently this packets key of job data is the previous packet, which is a pro argument. In that, if there is a text, yes, if there is a text, then what it does is it copies the existing text from it and it deletes the text key from the job data dictionary. And then if text is present in the task job data, which is the current con argument, if there is a text, so I'll copy that text along with the previously available text. I'll make it as an array and I'll create a new key known as tasks. So I have removed the text already, text key already, and I am creating a new key known as tasks. In that, I have put a array of two texts, one from the pro argument and one from the con argument. Now it will check again. It will come out of this if and else condition. Then it will check whether the length of this, right now it's only 2, but self.n is 3 because we have 3. One more is there, so it will not happen. So it will return again none. Then when third is added, which is like safeguard agent's output, so this whatever, like after two keys, after 2 tasks you have sent, the third task always will go to, from third task onwards it will go to this loop only, this condition only, this condition and this condition, it will not be met. So it will go to this, where we are trying to do a append of the currently tasks text content. So it will be added to this array. The third text is added, text is added to the array, and then again it will be checked. If it is n, then it will be returned. So it will take a copy of it, and then it will delete the self.packets and it will return. So now again self.packets will be empty before returning. So this is what the current mux is. Right now n is hard coded, and if you need a dynamic, we have some other examples for dynamic muxer. So right now this is a muxer where n is known at the runtime itself. So this muxer class, we need to give it, we need to initialize it, and in the agent's initialization, and then we need to pass on the muxer object. So before initializing, we require n value. So that value we are trying to take it from the our JSON file. So if you check our JSON file for the registration, so you have a persona config parameters mux size equal to 3. So that's what we are trying to read it. So config parameters mux size. So that mux size is initialized to the muxer class, and that object self.muxer will be sent as a muxer. So this object is taken care by agent SDK, the main.main, whatever we have here, right? Agent SDK core main.main. So it will take care of that object, and it will do a add function, and whenever it is adding a new packet, that packet is added to the self.packets, and a return of none will be sent when the first time. If it is done, again it will move on to receive the second input. Second input is read, and again adding is done by the muxer object, and again it will return a none. So since it is done, again it will wait for the third object, and if it is third object, text from the third agent, the third agent will add it, then it will become equal to the number of self.n, and then it will return a packet task. It will return a returnable task, and that task will be sent to the onData function. So here the onData function, what it does is it simply breaks the input to a text and model name session ID communication, and this text will be sent to the LLM with the signatures. The signatures, we have defined it clearly. You are a synthesizer balanced recommendation for pro, con, and safeguard inputs. identify the core technical tensions and trade-offs. Your output must objectively weigh the benefits against the risks. Structure consensus, area of agreement, dissent, trade-offs, significant risk, unresolved technical debts. So, and then action plan, concrete next steps, including must have safeguards before adoption. So this is the three outputs we are expecting from the this signature. This is the consensus synthesis is the output field, and mux context text is a input field. So once the final output is result is obtained, we will be simply passing that output to the agent grid. So agent grid will return back to the caller, which is user. So this is how the whole structure is. So let's start in running the use case. So we'll run the all bash dot agent registration. We'll run the all dot bash so that it will take care of removing if already available the agents are running. Then unregister it and register it and deploy the agents again. So let us start. So it is removed the old there's no old agents, but since it's an asynchronous, it will send a success message, and it's sleeping now because if agents are there, it will take some 20 to 30 seconds. If it takes more seconds, so you have to just update this. Now Docker is built and pushing to the registry, and all the agents are built. Like we require totally 5 agents. 5 agents are built and pushed to the registry, and registration is happening. Unregistration happens, then registration happens, then deployment of the agents will happen. So if you check it, now we are having 5 executors and 5 agent core pods. So let us check one by one. Let's go to the summarizer. So this is a consistent safeguard. So agent core is the instance ID. So right now I have all the 4 agents. Let me just run the input now. So input request I'm trying to trigger now. Yes, the input has been sent. So let us check the first agent. So yeah, first agent has got the input and it has generated the outputs. So yeah, but before that I'll just show you what is the input inference request. So here the input is we are trying to do a canary deployments instead of a blue-green deployment. So what all are the good and bad things about it? What is the guardrail? So it's asking basically that. So we have a blue-green deployment on Kubernetes. Rollbacks work, but cost is very high because you have a blue and a green. Both the deployment has to be available online. So then only the this costs them. So that's why we wanted a canary deployment where a phased manner deployment is required, like initially with 5%, then 25%, 50%, 100%. So what all pros are there, what all cons are there, and what all guardrails, securities, safeguardingness we need to have handle it. So all those things will be discussed. And the model that we are using is AI voice. It's a AI voice model only, and it is Qwen 3 1.7b. It's deployed using the help of VLLM Python. So that's the model, a very SLM, a very small model, 1.7b model only. So it is generating like say this is the input, RFC input is given, and reasoning and summary, we are expecting a summary from a neutral lossless brief of the RFC is required. so that it is generating here context service, add a candidate deployment to service X. It is generating a summary, and that summary is passed on to the next all the three agents. So all the three agents have generated their output, context text, reasoning pro arguments, and context text is input, reasoning and con arguments will be generated by this agent, and then from the safeguard context text, reasoning and safeguard has to be generated by the third agent. So now let us see the fourth agent, what it does, the consensus synthesizer. So this is the consensus synthesizer's output. Let me just take it to some thousands so that we can see a lot of messages coming out of. Okay. Okay, so this is the job input coming out of con argument. Similarly, we need to search for job inbox. So input for pro argument. So as you can see that the input has been received, but it will just add the task to the muxer agent. So muxer is added, but it will not do any other activities. It will move on. Then one more input is received from the con argument. Then it will be adding to the muxer again with the task ID. This is the task ID, and then again it will move on, and one more input has to be received. The safeguard argument has to be received. So once it is received, then only it moves on to doing the inference, like summarizing. So muxed content text, reasoning, and consensus synthesis. So you have a consensus synthesis output here, so that we will see it in the notebook. So yeah, this is the input and this is the output. So you can increase the number of tokens required from a JSON file as well. So you have the LLM parameters, right? So you can always increase the number of tokens, max token generations, to generate a more number of text if in case you want it. So that is a parameter, so you can always dynamically control as well. Not just during the registration, you can send it during the inference as well. So this is about the consensus synthesis. So it is saying, yeah, consensus synthesis, a proposed candidate deployment strategy with progressive traffic split over 60 minutes, leveraging Kubernetes service mesh is a balanced approach that reduces risk and improves reliability. It aligns with the goals of SLOs to rollback and cost efficiency, and includes the important safeguards. So dissent and trade-offs, so technical debt, operational overhead, risk of rare regressions, security blind spots, cost amplifications, all those things are in the dissent and trade-off where they are not agreeing, and this is the action plan. So this is what we have asked from the last one. So here we are asking for a consensus areas of agreement and dissent trade-offs, so significant risk and unresolved technical debts. This is what we need to discuss a little bit further. And action plan, concrete next steps, including must have safeguard before adoption. So that's what it has. Action plan, implement a phased rollout with the clear SLIs and baseline metrics, conduct thorough regression testing before deployment, set up automated abort criteria, real-time alerting for SLO breaches, monitor each phase of the rollout closely using Kubernetes service mesh, establish a rollback window, fallback mechanisms to ensure these are the safeguard rules, guardrails. And once done, if you want to remove those agents, right, so you can always choose the remove agent.sh. So if I run this right now, so it is getting terminated. All the agents are getting terminated one after the other. So this will take some time, but yeah, the agents are terminated now. So that's it for this video. So in this video we have basically saw how we can do a mux kind of operation where synthesizing is required. Let's say output of the multiple agents are muxed, and maybe the final agent, which can be a master agent or any other agent, it will try to do a synthesizing. And So I have explained a mux where n is very hard coded or static, and for the dynamic I'll explain you in the later section. Thanks for watching. Keep supporting us.